Section 4.3 is on modeling with quadratic functions. If you know 3 points on a parabola, you can write its equation in standard form. Here's an example. A parabola contains the point 0, 0, negative 1, 1, and 1, 5. What is the equation of this parabola in standard form? Recall that standard form is y equals ax squared plus bx plus c. So what I'm going to do is take each one of those points and plug those values in for x and y and try to determine what are the values of the constants a, b, and c. So when y is 0, I have a times x is 0 squared plus b times x, which is 0, plus c. This one's really nice because 0 squared is 0 times a is 0, so that goes away. B times 0 is 0, so that goes away. So that leaves me with c equals 0, which is really nice. So that's one of my 3 numbers I need to find. Now let's try negative 1, 1. So y is 1, which equals a times negative 1 squared plus b times negative 1 plus, and instead of writing c, I'm going to put in 0 for c because that's what I determined that to be. So that gives me 1 equals negative 1 squared is 1, 1 times a is a, and negative 1 times b is negative b. So that gives me the equation a minus b equals 1. Now let's plug in the point 1, 5. So when y is 5, I have a times 1 squared plus b times 1 plus c, which is 0. And that leaves me with 5 equals 1 squared is 1, 1 times a is a, b times 1 is b, a plus b equals 5, and that gives me another equation. And so here I have 2 equations with 2 variables, a pretty straightforward system of equations to solve. What I like about this is notice that the coefficients of b are opposite, so I don't even have to multiply anything. I can just add the 2 equations, and that gives me 2a is equal to 6, so a is equal to 3. Plugging that into this equation, 3 plus b is 5, so b is equal to 2. And so my final answer is plugging those values for a, b, and c into the standard form of the quadratic function. So y equals 3x squared plus 2x plus 0, which I'm not going to put on there. So given 3 points on a parabola, we can write its equation in standard form. Here's another example that uses a quadratic function. Campers at an aerospace camp launch rockets on the last day of camp. The path of rocket 1 is modeled by the equation h equals negative 16t squared plus 150t plus 1, where t is the time in seconds and h is the rocket's distance from the ground. The path of rocket 2 is modeled by the graph below. So here we have 2 rockets. The path of one of them is modeled by an equation. The path of the second one is modeled by a graph. And so what we want to know is, we have a couple questions about this. We want to know which rocket flew higher. So let's start with rocket number 2, which we have the graph for right here. So this is rocket number 2. Notice on the graph, my x-axis is time in seconds, and my y-axis is height in feet. So at this point right here is when the rocket took off, reached its maximum height, and then it started to come back to the ground. So it left here at 0, 0, reached its maximum at 6 seconds and probably about 580 feet, and then it came back and hit the ground 12 seconds after it was launched. So the vertex of this rocket, this launch, is 6, we're going to call it about 580. Okay, now let's do the same thing for rocket number 1. So rocket number 1 had the equation h equals negative 16 t squared plus 150t plus 1. And I want to find the vertex of this because its path is going to be very similar, but it's going to have a different maximum value, probably. So let's use our equation. Remember our equation, x equals negative b over 2a. That's going to give me the x of the vertex. In this case, I'm using t instead of x, so I'm going to go with t equals negative 150, which is b, over 2 times a, which is 16. And if I calculate that out, I get a 4.6875. I'm going to round that to the nearest tenth, and I'm going to go with 4.7. So that was its height. So the vertex of this rocket is going to be 4.7, comma, and then when I take this value and plug it back into here, I get approximately 352.6. I'm not going to show you the work on that, but if I plug in 4.7 for t into this equation, I get a height of 352.6 feet. So which rocket flew higher? The height of rocket number 2 was 580 feet. The height of rocket number 1 was 352.6 feet. So rocket 2 flew higher. Next question. Which rockets stayed in the air longer? Well, as we saw from the graph of rocket number 2, when it took off at 0, time was equal to 0, it reached its maximum height at 6 seconds, and then hit the ground 12 seconds later. So rocket number 2, it stayed in the air for 12 seconds. Now we don't have that information for rocket number 1, but we could actually do a little sketch of what it might look like. It is also going to have time in seconds and height in feet, and its graph is going to be a parabola, very similar. We do know that this point right here was 4.7, 352.6. So that means that right down here on the x or the t-axis, that value is 4.7. And we know that when it goes up, it's symmetrical when it comes back down. So this distance from 0, 0 to 4.7 is 4.7, and then from 4.7 to when it hits the ground is another 4.7 seconds, and that's going to be 2 times 4.7, or 9.4. So rocket number 1 was in the air for 9.4 seconds. So in this case, again, rocket number 2 comes through, staying in the air for 12 seconds. When more than 3 data points suggest a quadratic function, you can use the quadratic regression feature on your graphing calculator to find a quadratic model. Here's an example. The table below shows a meteorologist's predicted temperatures for a fall day in Baltimore, and we want to know what is the quadratic model for this data. So I'm going to use the data in my time column, and I'm going to put that into list 1, and then I'm going to put my predicted temperature into list 2. Now let's take a look at the time here. So I have 8 a.m., 10 a.m., 2 p.m. So I can't really put in 8, 11, 2, 5, 8, and 11. That's not going to work. What I need to do is kind of think in terms of military time. So 800 hours, 1100 hours, 2 hours after 12 noon is 1400 hours. So I'm going to go list these numbers here. So I want 8, 11, 14. 5 p.m. is 5 hours after 12, so that's 1700 hours. 8 p.m. is 2000 hours, and 11 p.m. is 2300 hours. And then I'll just use my temperatures here. Okay, so here's a good question. So how do I know that this data suggests a quadratic model, that it's going to look like a parabola? Well, let's look at my y values here, my predicted temperatures. At 8 in the morning it's 52 degrees, and then it warms up to 59, and then it warms up to 63, stays at 63, maybe went a little higher in there, we're not sure, and then it starts to cool down again. So my values are going up, and then my values are coming down, and they're kind of symmetrical, so there is a little symmetry there. So I'm going to go ahead and put these into my calculator. Okay, so here's my calculator. So again, I'm going to hit the stat button, and that brings up my stat menus here, and I'll hit enter, and you can see that I've put my x values, my time of day, into L1, and then I put my temperature into L2. So let's go ahead and hit stat, and I'm going to go over to calc. And remember, a couple chapters ago we were using this linear regression. Now we're going to use quadratic regression. So I'm going to go down to 5, and it's going to ask me, or kind of defaults to my list. My X list is going to be list 1, my Y is going to be list 2. Make sure you don't have anything here in frequency list or the store reg equation. And let's arrow down to calculate and hit enter. And here it gives me, it's taking a little bit of time, it's going to give me my equation in the form of y equals ax squared plus bx plus c, and it gives me values for a, B, and C, and again an R value that tells me how close it is, which is actually pretty good at 0.9. Okay, so let's go back to page here. So the quadratic model that I had for this was y equals, my a was, I'm going to round it to negative 0.16 t squared. Oh, you know what? Let's go with x. You go ahead and use x. X squared plus, I'm going to round it to 5.14x plus 21.6. So just using my calculator, that's the quadratic model for this function. And at what time will the predicted high temperature occur? So remember, this is going to look, since this is an upside down, it's going to look like this. Okay, my graph. What time is the high temperature going to occur? So in other words, what is the x of the vertex right here? So I'm going to do x equals negative b over 2a, or negative 514 over 2 times negative 0.16, and that gives me 16.0625, or approximately 16. But remember, what does that mean? That's 1600 hours, so that's at about 4 p.m. in the afternoon. And just out of curiosity, what would my high temperature be at that time? So I'm going to put x into the function, or put that value, put 16 into the function, and when I do that, I get that y is approximately equal to 63. So at 4 p.m., the temperature is approximately 63 degrees. So in this section, we took a look at how to model some real-life situations with quadratic functions and how to use the quadratic regression feature on your calculator.